So if I do NP hat, I get 459. That's at least 5. If I do NQ hat, I get, what do I get? 193? 2? 993 then. Great, equal to 5. I like it. So again, either you understand that NP hat will always be the number of successes, and that makes it nice, or you don't. You just do the work. Who cares? Either way. I want to be 96% confident. We actually looked at the work for that earlier with a problem from the book. Yeah, so if I want to do this, 0.02 is here, right, from earlier. And what do you get again? 2.05? Okay. You guys can double check that. That sounds about right to me. 95% would be 1.96. So 96% will be a little bigger than that. It's got to go a little further out, so 2.05 makes sense at least that far. You guys with me a little bit? Do you remember 95% is 1.96? What's up?
1.75.
Yeah, is it 1.75 the z-score?
No, hell no. So, let me borrow a z-score chart real quick. I think I gave all mine away. Or maybe I have one somewhere. What am I looking up? I'm not looking at 0.04, right? I'm not looking at 0.04, am I? No, I'm looking at 0.02, right? So if I look up 0.02, closest I get is here. Do you guys see that? 1.75. Let's see what happened with 1.75. Ah, so you looked up 4. Okay, that makes sense. Thank you for circling that.
What number are we? Okay.
I love you guys so much. 96% inside means how much on either side? 0.02, 2%. So if you look up 2%, you're going to find this z-score, which means the other one is the positive one, right? Symmetric, boogie woogie. So if you look up 0.02, the closest I can get is right there. And like she said, that's 2.05. Why do I not care about the negative? Because it's built in. It's right there. It's built into the formula, the positive and the negative. All I care about is the number. So that is 2.05 for damn sure. Everybody with me? So confidence intervals always chop off the middle. You got to do half of what's outside to be just on one side. Yes, Brandon.
So you looked at 0.02. So how did you know to do that on the negative side?
Oh, two reasons. The positive side starts at 0.5, so that's kind of a giveaway. The other thing is I'm looking at this z-score, which is below the mean, so it's going to be negative. Right?
Okay.
And again, watch this, you guys. You don't have to do what I'm about to do. But what if I wanted to find this z-score instead? Can anybody tell me what percentage is below this z-score total? What total percentage is below this z-score? 98. If I look up 0.98, guess what I'm going to get? 2.0 frickin' 5. Of course I'm going to get 2.05 because it's symmetric. It doesn't matter which z-score you find first. It's just a little quicker to find the negative one first.
So
Yes?
why are we not putting negative? I get that it's included.
I love it. Now watch. This is negative 205. It totally is, right?
Yeah.
And this is positive 2.05. But when I say what's the z-score I'm going to use, I put 2.05 because the plus or minus is built in. I just don't want somebody putting a negative there for z and then freaking out about what that does. How do I know that could happen? Because it's happened. So I try to make a big point of that so that it doesn't happen. The plus or minus is built in. You just care about the number. And now we got everything we need. P hat 0.704, give or take this many of these. I didn't need that. Oh well. 704 times 0.296 divided by. The other big mistake people make is they put the smaller number here that doesn't make any sense. N is always the total that I'm looking at. So N is always the bigger number. So let's see what we get for the error. If you do the error.
I got 0.0366.
0366? Let's see. Let me catch up to you. Yeah. 0366, 037. And then you just add that, subtract that, make the interval.
0.667.
Yeah, 0.667 up to 0.74. So see, that looks very much like what we're used to. That's roughly 4%, give or take 4%, right? So I know, again, going back to that comic on the grade sheet summary, that's me. I'm very excited. This is so cool. We finally know how to calculate that little plus or minus thing they always put on every poll ever. And they don't just pick a number to cover their ass. They use the number they get from doing this formula. So why do some people have smaller plus or minuses? Because they might have had a bigger sample, or they might have wanted to be less confident. Maybe. So then we are 96% confident that the interval 66.7% to 74% contains the true percent of people who voted in the last election. I like it. People who voted, that's enough. That's all the box I got. And that, of course, is the most exciting part of the problem is he wants me to write paragraph? It's not. It's one sentence, right? And I don't grade you on grammar. I did have a math person that would grade us on grammar. I'm like, keep those worlds separate. Whatever. Okay. So, I'm not going to run through the algebra of this. I'm hoping that most of you guys could do this. If you square both sides of this, multiply by n, divide by e, you get this thing. If you don't believe me, you can try it. If you don't want to try it, okay, there it is. But it's good old algebra comes in and saves our ass. And this is the same formula related to the one we had for means. How big of a sample do I have to take to be within something? It's what Weird Ass Jeff calls a feasibility study. If it comes out to be 7 million, I might not be able to do that. Right? So what do I tell you that's going to help you fill this stuff in? Well, I don't tell you what P and Q are, but of course, when you don't know, your best guess is 50-50. How do I get Z? Yes, 99%. We just did one like that. That was 2575. And then what's E going to be? What do I want to be within? How much? What percentage?
103.
Good. 3%, which is 0.03. Some of you guys still don't change your percentages. Don't shove any percentages into an equation, because that's not the number. The number is the decimal. Percentages is something we made up to make numbers easier to look at. They're not the number. So don't put 3 in this bad boy, or you're going to get the n has to be 0.7. You have to take 0.7 people. Holy shit. And that's how you become Dexter. You just start chopping people up. It's no good. So, that's where So now we got everything we need for the formula. N is 2.575 squared times 0.5 times 0.5 divided by E squared. One big thing is people forget, besides making this not into a decimal, they forget to square that too. So see what we get here. Tubular. I like it. Tubular. What'd you guys get for this? Let's see.
42.9.
42.9? God, I can't see shit here. Let's see. Wow. Oh, did I do that right? Yes.
125.
Wait, what did?
All right, sorry. Let me do it. What's half times a half? What's a half times a half? What's a half of a half? A quarter. 0.25. So 0.5 times 0.5 is 0.25. I think in the book, you're going to see a formula with a 0.25 there. And that's where it comes from. Because when I don't know P hat and Q hat, I guess 0.5 for each, which means that when I multiply them, I'm going to get 0.25. And then 2.575 divided by 0.3, and then I just squared both of those. I got 1841 point something. And it doesn't matter what that point anything is, I make that 1842.
Oh, it's weird.
Sorry? Say again?
That'd be
Error is how much I'm off by. So that's why the word within might not always be used, but when it is, it's a huge clue. That's your error. I want to be within 3%. I want to be off by 3%. I want my error to be at most 3%.
plus minus within.
Plus or minus what?
Like within would mean.
Oh, yeah, good. That's how much you add and subtract. That's the error. That's what within means. So they won't always use the word within, but when they do, that's what the error is, because that's what error means. So I'd need 1,842 people to ensure that I'm within 3% of the true proportion, which kind of makes sense. Up here, we took 652, and we were within 3.7%, right? So let's see. What if we had done this? So if we'd done a preliminary study, so you guys, I don't know where the hell I'm from now. You guys have all heard the phrase preliminary study?
C.
Okay, maybe. One Spanish person. So why do we do them? One reason is so we can get a better feel. Remember what I said about if I make these 0.5, it makes n the biggest it might have to that it has to be. So if I have a little bit of information, I do a little tiny preliminary study, I could put actual values in there and get a better estimate for n. So from this study, what's p hat? I don't have to guess anymore. I know what p hat is. How do I get it?
31 divided by 42.
Yeah, 31 over 42.
0.738.
738. So what's Q hat?
0.262.
262. I like it. Everybody see where that came from, right? No matter what article of clothing they're wearing, P and Q have to add to be 1. We know that because of what they are. So now I could do the exact same formula, but instead of putting 0.5 and 0.5, I put 0.738 and 0.262. Where'd it go? E was 0.03 still. That's right. So same formula, right? Here we didn't know shit, so we had to guess 50-50. Here we know shit, so we put that shit in there.
Still 99% confidence.
Yeah. Sorry, it's all one big problem. On number 2, yeah. So let's see what we get here. I'll just do this. No, Jeff, do it all over again. Okay, yes, sir. I swear to God. Hello. All right. Oh my gosh, that was harder than it should have. So you put it all in there. Let's see what we get. Yay! we have to talk to about 400 less people. Okay. So now I just need 1424 points. So I make it 1425. So to be honest, I don't mean this as a trick question, but you guys see that's not really the answer? Does anybody notice how that's not quite the right? If you stop there, I'm going to give you full credit. But look at the question again.
You subtract the top from the bottom.
No. If we had done a preliminary study of 42 students, so we already talked to 42. So I can subtract 42 away from this to see how many more. I'm not even going to do it. If you forget about that, I don't mean that as a trick question. Just when you do a preliminary study, you already have some data. So you can just add on top of that data to whatever else total number you need. So I got 400 less people that I got to talk to. That's not bad. That's why we do preliminary. That's one reason why we do preliminary studies. I want to show you something. Come on, you can do it. Okay. These sound effect. You just need help. You do it. Just go away from there. There we go, buddy. One more. Oh, dude, you did it. All right, good. This, by the way, not to be controversial or anything, I don't give a shit anymore, is approval for impeaching Trump. So if you look at the bottom, if you want to see what that is, it's over half now. However you feel about that. So you can see, the beautiful thing about Gallup is they really go deep into how they did things. Deeper than anybody else, just about. Results for this are based on telephone interviews with a sample of 1,526 adults. Plus or minus 3% error at the 95% confidence level. So I want you to realize that the work we are doing right now in a Stats 1 course are pretty much exactly what they're doing with a preliminary study like this, right? Now, to be really honest, there's a little bit of tweaking there for weighting, and they had to be careful about the fact that they did telephone interviews, so they didn't get everybody. So there's these little tweaks you could do to the formula to account for that. But the basic underlying idea is that, the p hat plus or minus blah, blah, blah. Okay, and again, I go back to my comic. I'm still excited about that, and you're all like, well, that's great. Okay, so now we're going to do the thing that you just can't wait for. I promised you guys remember how I said that I skipped section 8.2 because it involves a different distribution. Now, to maybe pull some of you guys back in, anybody drink Guinness? Anybody know Guinness? You guys know what Guinness is? Anybody drink it or anything? Say again? It's European, yeah. So, a lot of our physics professors, when I was going to grad school, they drank Guinness, so they would invite us out to the bar after class, and we'd all sit around and talk about how with little we understood, and they'd all laugh, and they'd get drunk, and they'd feel better. And I don't know, we just put up with it. I don't really like Guinness, to be honest. But what does this have to do with anything, Jeff? Well, where this distribution came from. There was a guy named William Gossett who worked at the Guinness Brewery, which is a fun word. And he did this analysis, and I forgot to look it up. I can't remember exactly what it was about. But he did this analysis, and the thing is, since he worked at the brewery, anything he did was their property. So what he did was he put this analysis out under a pseudonym. He's called himself Student. So what this was all about was he didn't know the population standard deviation, and I think this was fermentation times or something. So he had to take a sample standard deviation. Now listen, stay with me. If you don't like Guinness or anything, that shit. If there's something about the equations we're working with that we're not sure about, we have to cover our ass for that somehow. So if I had a confidence interval sitting there and there was something in it that I wasn't sure about, like something that went into the equation that I wasn't sure about, should the interval get bigger or smaller to account for that uncertainty? We could do this. It should get bigger, right? And again, I like it because then I can cover our ass for the thing we don't know. If there's something I don't know, it should have to get bigger. So all this is kind of cool. It boils down to this. I can't use a z-score when I know sigma. I have to use a score that's a little bigger. Because what did we just say? If there's something I don't know for sure, I've got to make my interval a little bigger. And the most direct way to do that is to make the score I put in for z a little bigger. So looking at the formula, if I make Z, holy shit. Want this to be like an Etch-a-Sketch thing where, so looking at this bad boy here, so what I'm saying is, when I don't know sigma, when I only know S, I can use it. It's a good estimate for sigma. But to cover my ass for that, I can't use a z-score. I have to use some kind of score that's always a little bit bigger. And again, hopefully you guys, even if you didn't say it, it makes sense. If there's something that goes into my interval that I don't know for sure, I should make my interval a little bit bigger to cover myself for that. It's kind of like a punishment. So what we end up putting here, I just gave it away earlier, when he submitted this research he did, he constructed what's called a student's T distribution. It's a T-score. I love your face right now. Like, I promise you this, is only after the chart I give you today, and yes, I have a T-score chart for you. Fantastic, Jeff. That's exactly what I want. There will just be one more chart after this that I give you later in the semester. One more chart after this. Somehow it has something to do with Dragon Ball, but we'll get there. Okay. So, for example, if I wanted a 99% confidence interval and I knew sigma, I would put 2.575 there, like we just did. But if I didn't know sigma, I have to put something there that's bigger than 2.575. Okay. Now, if I took a sample of, let's say 40, and I got an S, and somebody else took a sample of 400, and they got an S. Is everybody with me? So I took a sample of 40, somebody else took a sample of 400. Which one of us is more certain about their S, is more certain about their standard deviation that they found?
Smaller.
400.
I love you guys so much. What makes sense? What makes things more certain? A small sample or a big sample?
Big sample.
Yeah, so which one of us is more certain about the standard deviation we found? I'm with you, but not everybody said 400, right? This one. So whatever this score is, whatever this T-score is, not only should it be bigger than Z, but it should get even bigger as my sample gets smaller. Because the smaller my sample, the bigger the thing has to be to cover my ass for not knowing this, because I'm even less and less sure about it. Okay, so here we go. Let me give you this bad boy. Just what you wanted. One more chart to keep track of. You didn't have to ask me. I knew you wanted it. So, let's look at this thing. Let's figure out what the shit this is talking about. Oh, check. So notice a couple things. Look at the very bottom. Does anything look familiar? The numbers at the very bottom of the chart. Anything here look familiar at all?
Yeah.
1.645, right?
Yeah.
1.96. 2.576, it's a little bit more specific. 2575 was from the z-score chart, which isn't quite as specific, but it's still 2575 like we just saw, right? And then there's this new one, 2.326. Okay. So those numbers look familiar. Those are z-scores. So again, do you see what happens? So if my sample, and how big is the sample in that bottom row?
Over 2 grams.
True, but what is it officially? Large, right? Why do they say just large? Because it depends on the situation. If it doesn't really matter that much, you can use it no matter. But if it really matters exactly, then you want to be more specific about what large is. So some people large would be over 2 grand, and some people large isn't until you get to 50,000. So then you can use T-scores all the way, right? So do you guys, one thing to notice is, so here's the 2576, like the 2575 we just used. That's a z-score. So that's one neat thing about the T-score chart is that it has z-scores in it. What happens as my sample gets smaller and smaller? It gets bigger and bigger to cover my ass because the S we get is less and less certain. It could be further and further away from the real population standard deviation. So as my sample gets smaller, then my T-score gets bigger. Because the smaller my sample, the more I need to cover my ass for not knowing what the real standard deviation is. Okay, maybe. Notice this too. So how the hell do you read this thing? So there is something called degrees of freedom. I could take away my dignity. Just gotta take my degrees of freedom. So, let me see if I have paper. Paper. No papers. You got paper somewhere. There you go. All right. Do you guys remember back in the day when we had this formula here? Remember that? And then you remember there was a slight difference for this one? Because, of course, this one means what? Sample standard deviation, right? What was it divided by? Anybody remember? Not n. N minus 1. And at the time I said that was just an adjustment. And this is not false. It is an adjustment for it just being a sample. But now I can give it, I don't remember if I called it what it is. But let me show you why it is called degrees of freedom. Degrees of freedom. So if I had 3 numbers, and I knew that their average is 10. So I got 3 numbers, and I know they average to be 10. Do you know what any of the numbers are? You don't have a freaking clue. But do you know what they add up to be? They have to add up to be something. So if I have 3 numbers that average to be 10, what do they have to add up to be? What do you divide by 3 to get 10? How do you average the numbers? You add them up, divide it by 3, gives you 10. 30. So I know they have to add up to be 30. So how much freedom do I have to just make shit up? The first number, what could it be? It could be anything, right? Let's say the first number is 1, yeah. And the second number, it could be anything. Who gives a shit? Let's make the second number 20. But then the third number has to be something. What does it have to be? 9. That's crazy. So how much freedom did I have? Did I have 3 degrees of freedom? Did I? How much freedom did I have? Just 2. N minus 1. I had N minus 1 degrees of freedom. That's why we call N minus 1 is called the degrees of freedom. There's a little formula for you. Degrees of freedom is N minus 1.
Can you like zoom out because I want to get the.
So in the chart, they didn't have to do this, but they did. They used degrees of freedom on here because it is an important idea. It goes along with a lot of what we're doing. Just to remind you guys, I do record these lectures, so it's up there on the internets and the YouTubes. So you see degrees of freedom? So how big is the sample in the first row really then? How big is the sample? 2. Because 2 minus 1 is 1. Do you guys see that? So if I had a sample of 11, where would I go? 10. Because this is degrees of freedom, which is n minus 1. Okay, I like it. All right. Now, there's this idea how to read this shit. Do you see how there's 2 rows? So help me out. Let's double check this crazy ass chart that Jeff is trying to push on you. Jeff and his freaking charts, wasting paper in the universe. 95% confidence interval. Can you draw that for me? What does it look like? Well, it looks like this, right? Weehaw! Some little ghosty dude. And where's the 95%? Chop, chop. Let me see if I ask you this. How many tails did I just make? 2-tailed. It's a 2-tailed thing. How much area total is in the 2 tails? 0.05. And do you guys remember, for the 95%, isn't that 1.96? If you don't trust me, you can look at the little baby chart on the z-score. Some of you guys might remember that. So let's double check with this thing. So notice how these are z-scores, and I'm going to use the t-score chart to verify it. Why? Because z-scores are at the bottom. So what situation am I in? In 2 tails, there was how much? 5%. So 2 tails, 5%. If you go all the way down, you get a z-score. If you stop somewhere, you get a t-score. Because the bigger the sample is, the less you need it to be bigger than z, so that when your sample gets large, you can just go ahead and use a z-score instead. Because what's the purpose of a t-score? To cover your ass for not knowing sigma. Well, when do I get more and more sure that my S is close to sigma? When my sample gets really big. So when my sample is freaking huge, I could just go ahead and use a z-score. That's why z-scores are on this thing. So do you guys notice, what confidence level would this be? If there's 2% in the tails, what's inside? 98. That's a 98% confidence. That's a 99% confidence. You guys see that? No? And the beautiful thing is, even if you look at this incorrectly, how much is in 1 tail on this 95% confidence? 0.25. No matter which way you look at it, 2 tails, 1 tail, you're in the same freaking column. Do you guys see that? Even if you look at it wrong, you're looking at it right.